All of you have been through the conservation of energy before and its formulas. So I'm not going to spend a whole lot of time explaining that again. With that being said, one of the main issues I see in student work is the sign convention of energy. Students often subtract when they should be adding. They're showing negative values when they should be positive. So I'm going to introduce a method used in our book to hopefully keep those problems from happening. Let's get started. This is the conservation of energy equation introduced in our book. We have T1, which T is the letter used for kinetic energy. Why do they use the letter T? I'm not sure. All right, but I'm going to use the same that they use in the book. If you want to use KE, you can, but just to know when you're reading the book, the capital letter T means kinetic energy. All right, so we have kinetic energy plus all the work being done from state 1 to state 2 equals the kinetic energy at state 2. Okay, all of you know that the kinetic energy term is 1/2 mv squared. So on the left-hand side, we have 1/2 mv1 squared, and on the right-hand side, we have 1/2 mv2 squared. Okay, so what is changing this kinetic energy? All of our work terms in here. So these could be things like forces. This could be weight. This could be a spring. All of these things, in terms of work, alter our kinetic energy from state 1 to state 2. This is a very quick example of how to use conservation of energy. So we have a block being moved here by a force P, and it's moving from position S1 to S2. It has an initial velocity of V1, and we also need to take into account the normal force and the friction force here, which we're going to call mu sub k times n. All right, so what we have here is a simple setup. Now let's use the kinetic energy or the conservation of energy formula to solve this. So we have T1 plus the sum of all the work from 1 to 2 equals T2. So T1 is easy. We just have 1/2 mv1 squared. So m being the mass of this block, m. And then we have all the work terms. So what are all the work terms? Well, we have, remember that the work terms only contribute if the force is in the direction of movement. So for example, the weight term and the normal term are 90 degrees from the direction of movement, and the cosine of 90 degrees is 0. So neither of those contribute. So we have our force P being applied, and that is the distance that it acts upon is S2 minus S1. And then we also have this friction term, all right? And since the friction term is opposite in the direction of movement here, opposite in the direction of movement, that would be a negative work term. So we have mu sub k times n, and then we have S2 minus S1 there. Okay, and then those are all the work terms that contribute, and the right-hand side then equals 1/2 mv2 squared. And this is a simple example of how we apply the conservation of energy to this problem. Now, in the conservation of energy equation that I just introduced, this may be making you a little nervous because every time in the past when you've done conservation of energy, there's been a potential energy term. And in our equation, there is no potential energy term at all. So where is the potential energy in this equation? Well, we factored it into the work term. The work term, remember, for moving the height of a weight here, we said that this work term is negative W times delta Y here. So the potential energy that you've always seen in the past is built into this work term. All right. The book goes on to break out potential energy from the conservation of energy equation. So they offer this alternate form of the conservation of energy, which is T1 plus V1 plus the sum of the work from 1 to 2 equals T2 plus V2. right? We've already been through that the confusing nature that T is the kinetic energy. Well, it's just as confusing because they use V as the potential energy term. So what sort of things can we put into this potential energy term? Well, if we want to add weights into this and the movement of height, we would add things like mgh1 over here. And then we need to make sure we have mgh2, where 1 and 2 are the respective heights at state 1 and state 2. Okay, we can also add in the potential energy terms for a spring, right? We can move the spring equations to the potential energy, where we have 1/2 ks1 squared on the left-hand side, and then 1/2 ks2 squared on the right-hand side. So those could also be potential energy terms. Okay, so if you're more comfortable with this equation, go ahead and use it. The one thing I must mention is be cautious about where your terms are, all right? Do not overcount your potential energy terms. For example, if you put mgh1 and mgh2 in the potential energy terms, do not put W delta Y into the work term. You're double counting it. So that should not be included if you put the weight into the potential energy terms. So what is this term used for? Well, you can think of this term being used for, let's say you have a force applied P over a distance, or you could use this for friction here. That's what the work term here would be used for. All other terms you could factor into the potential energy terms.